Hello! In this video, we are going to prove the extreme value theorem, which says the following. Suppose f is a function from the closed interval a comma b to r, and f is continuous on a comma b. Then, f attains a maximum value and a minimum value on a comma b. Now in this video, we are only going to show that f attains a maximum value on a comma b. Now in proving this theorem, we are going to be using a result which we have proven, and it's that since f is continuous on a comma b, it follows that f is bounded on a comma b. And since f is bounded on a comma b, it follows that f is bounded on any subset of a comma b. Now, just to explain what's happening here, to say f is bounded on a comma b means that the set of output values, f of x, where x is an element of a comma b, is a bounded set. But any subset of a bounded set is bounded as well. And the idea is, for each element p in a comma b, we consider the set of output values, f of x, where x is an element of a comma p. Now, this is a subset of this. So since the set of output values from a to b is a bounded set, it follows that the set of output values from a to p is a bounded set. And by the completeness property of the real numbers, it follows that this set has a least upper bound. And for each element p in a comma b, we are going to let mp be the least upper bound of this output values f of x, where x is an element of a comma p. So then, in particular, mb is the least upper bound of the output values of f over the entire domain. So, mb is greater than or equal to every output value of the function f. But if we can show that mb is itself an output value of the function f, well, that tells us that mb is the greatest output value of the function f. So mb is the maximum value for f. So the whole goal is to show that mb is an output value of the function f. Now, if mb is equal to f of a, then we're done. Now we know mb is greater than or equal to f of a, no matter what. But if mb is equal to f of a, then we're done. So from here on out, we are going to assume mb is strictly greater than f of a. And in this case, again, we want to show mb is an output value of the function f, because that will tell us mb is the maximum value for f. And the idea is we consider the following set. We consider the set S, which is the set of elements p in a comma b with the property that mp is less than mb. And what we're going to do is we're going to show that this set is non-empty and bounded above, because that will tell us by the completeness property of the real numbers that this set has a least upper bound. Now, to show that S is non-empty, we're going to show that A is an element of S. So to show that A is an element of S, we want to show that MA is less than MB. But what is MA? Well, replacing P with A, MA is the least upper bound of the output values of F over A comma A. Or in other words, it's the least upper bound of the set of f of x, where x is an element of a comma a. But clearly, this set only consists of one element. It consists only of f of a, because this is really the set of f of x such that x is equal to a. So, this is the least upper bound of a set consisting only of one element. And it's kind of trivial, but this is just equal to f of a. And let me just explain this a little bit. The reason why is because this is the least upper bound of a finite set. But every non-empty finite set has a maximum element. Now in this case, f of a is the only element of the set, so certainly the maximum element of the set is f of a. But whenever a set of real numbers has a maximum element, that maximum element is the supremum of the set. So that's how we know the supremum of the set is f of a. So ma is equal to f of a. And by assumption, f of a is less than mb. So this shows ma is less than mb, which is exactly what we want. And that tells us a is an element of S. So S is non-empty. So we know that S is non-empty, but also S is bounded above because every element of S is less than or equal to B. So S is bounded above by B. So since S is non-empty and bounded above, well then by the completeness property of the real numbers, that implies S has a least upper bound. And we're going to let U be the least upper bound of S. Now, since U is an upper bound of S, that tells us U is greater than or equal to every element of S. So in particular, U is greater than or equal to A. But also, since U is the least upper bound of S, that means U is less than or equal to every upper bound of S. So in particular, U is less than or equal to B. So this shows that U is an element of A comma B. So since U is an element of A comma B, U has an output value through the function f. The claim is that MB is equal to f of U. If we can show that, then that will tell us U is the maximum value for f, and we're done. And to show this, well, remember, MB is greater than or equal to every output value of the function f. So we know MB is greater than or equal to f of U, no matter what. So, to prove that MB is equal to f of U, we'll assume for a contradiction, we instead have that MB is strictly greater than f of U. And to reach a contradiction, we're going to split this up into two cases. Either U is less than B, or U is equal to B. And in either case, we're going to reach a contradiction. We're first going to consider the case U is less than B. So then, how are we going to reach a contradiction? Well, we're going to be using the fact that f is continuous on A comma B. This just means that f is continuous at every point on A comma B. So in particular, since U is an element of A comma B, we know that f is continuous at U. And by definition of continuity, to say that f is continuous at U means the following. It means for every epsilon greater than 0, there exists a delta greater than 0, such that for all x in the closed interval A comma B, if absolute value of x minus u is less than delta, then absolute value of f of x minus f of u is less than epsilon. Now, let's sort of think about what's going on here and how we're going to reach contradiction. Let's consider the closed interval A comma B. Now, since u is less than b, let's just say that u is about right here. Now, the idea is, since f is continuous at u, and the output value of u through f is less than mb, well then we should be able to find a neighborhood around u small enough so that every output value in that neighborhood through f is also less than mb. In fact, we should be able to find a neighborhood small enough so that every output value in that neighborhood is less than the average of mb and f of u. So let's say that neighborhood is here, and it's bounded by u minus delta and u plus delta. So when we take any element of that neighborhood and send it into the function f, well then its output value will be less than the average of mb and f of u. And this is less than mb. Now, u is the least upper bound of s, so anything smaller than u is not an upper bound of s. So in particular, u minus delta is not an upper bound of s. Because u minus delta is not an upper bound of s, that means u minus delta is not greater than or equal to every element of S. Instead, u minus delta must be strictly less than some element of S. And let's call that element E. So E is an element of S. And since E is an element of S, well, this means that ME is less than MB. Right, so ME is less than MB. But what do these things mean? This is saying that the least upper bound of the output values of F from A to E is strictly less than the least upper bound of the output values over the entire domain, right? That's what this is saying. So then what is that telling us? Well, if we take any element from A to E and send it into the function F, well then, the output value is going to be less than ME, and let's note that's less than MB. Now to reach a contradiction, the idea is we can find an element in S that is bigger than U, but that'll contradict the fact that U is an upper bound of S. The idea is we could show that any element in this neighborhood to the right of U is an element of S. So for example, let's consider U plus delta over 2. We're going to show U plus delta over 2 is an element of S. To do that, we would like to show M U plus delta over 2 is less than MB. And the idea is, if we consider any element from A to U plus delta over 2, well then, its output value through the function F is either less than or equal to ME, or it's less than MB plus F of U over 2. But no matter what, it's always less than or equal to the maximum of ME and MB plus F of U over 2. But since both of these guys are less than MB, their maximum is less than MB. So what this tells us is that this quantity is an upper bound for the output values of the function F from A to U plus delta over 2. But the least upper bound of the output values of F from A to U plus delta over 2 is precisely M U plus delta over 2. So since this is the least upper bound, it must be less than or equal to this upper bound. And this guy is less than MB, so this shows that MU plus delta over 2 is less than MB. And that tells us U plus delta over 2 is an element of S. But since U is an upper bound of S, that gives us a contradiction. So that's how we're going to reach a contradiction in this case. So since F is continuous at U, this means we are given that this statement is true. And this statement works for every positive real number. So in particular, it must work for the positive real number MB minus F of U over 2. So taking epsilon to be MB minus F of U over 2, then there exists a delta greater than 0, such that for all x in A comma B, if absolute value of x minus u is less than delta, then absolute value of f of x minus f of u is less than MB minus F of U over 2. Now, if we consider any positive number smaller than delta, then this statement will still be true. For example, if we consider delta over 2, well, it is indeed true for all x in A comma B. If absolute value of x minus u is less than delta over 2, then absolute value of f of x minus f of u is less than this quantity. Right, so we can make delta smaller and smaller and smaller. This statement will still be true. So it's safe to assume that delta is less than b minus u. Now, just to see what's going on here, if we consider the closed interval a comma b, and we'll say that u is right here. Well, all this restriction is doing is it's assuring ourselves that the delta neighborhood around u will be in such a way that the right endpoint is to the left of b. That's all that this restriction is doing, is it's making it so that the right endpoint of this neighborhood is to the left of b. And because the right endpoint of the neighborhood is to the left of b, that'll assure us that u plus delta over 2 is in the closed interval a comma b. right? We need u plus delta over 2 to be in the closed interval a comma b, because that's a requirement to show that u plus delta over 2 is an element of S. Because if the neighborhood was too big, then u plus delta over 2 could be to the right of b. So that's the reason why we have this restriction. But then, why did we take epsilon to be mb minus f of u over 2? Well, because this is going to lead us to showing that every output value in this neighborhood through the function f will be less than the average of f of u and mb, right? This is just preparing us for that. But then, since u is the least upper bound of S, anything smaller than u is not an upper bound of S. So in particular, u minus delta is not an upper bound of S. And since u minus delta is not an upper bound of S, from our discussion, this means we should be able to find some element E in S, such that u minus delta is strictly less than E. And since u is an upper bound of S, we know that u is greater than or equal to every element of S. So in particular, u is greater than or equal to E. Now the idea is we can reach a contradiction by showing that u plus delta over 2 is an element of S. And here's how we do that. We want to show u plus delta over 2 belongs to the closed interval a comma b, and we want to show mu plus delta over 2 is less than mb. Now to see how u plus delta over 2 belongs to a comma b, well, notice we have that a is less than or equal to u, which is less than u plus delta over 2, which is less than u plus delta, and this inequality tells us u plus delta is less than b. So this tells us u plus delta over 2 lies between a and b, so u plus delta over 2 belongs to the closed interval a comma b. And our claim is that u plus delta over 2 is an element of S. To show u plus delta over 2 is an element of S, we want to show that mu plus delta over 2 is less than mb. And to do that, we're going to follow what we were looking at in our scratch work. Let's consider an arbitrary element x from a to u plus delta over 2. Now, if x is less than or equal to e, well then, x belongs to the closed interval a comma e. But then this means f of x is less than or equal to the least upper bound of the output values from a to e. In other words, f of x is less than or equal to me. And let's note, since e is an element of S, we have that me is less than mb, and that's what we have if x is less than or equal to e. So then what happens if x is greater than e? If x is greater than e, well then we have u minus delta is less than e, which is less than x, which is less than or equal to u plus delta over 2, which is less than u plus delta. So that tells us x lies between u minus delta and u plus delta, but from properties of absolute values, that tells us that the absolute value of x minus u is less than delta. So since absolute value of x minus u is less than delta, it follows that absolute value of f of x minus f of u is less than mb minus f of u over 2. But then, the idea is that this should imply that f of x is less than the average of mb and f of u. Right? The reason why this happens is because we know that every real number is less than or equal to its absolute value. So in particular, f of x minus f of u must be less than or equal to its absolute value. This guy is less than mb minus f of u over 2, so that should imply f of x minus f of u is less than mb minus f of u over 2. But then, if we add f of u to the other side, we get f of x is less than the average of mb and f of u. So that's how we get that. And since we're assuming mb is greater than f of u, well, the average of mb and f of u must therefore be less than mb. So, what this shows us is no matter what element x in a comma u plus delta over 2 we have, it is always either the case that f of x is less than or equal to me, or f of x is less than mb plus f of u over 2. So no matter what, f of x is less than or equal to the maximum of me and mb plus f of u over 2. But remember, both of these guys are less than mb, so their maximum must be less than mb. So what is this telling us? This is telling us that the output values of the function f on this interval are all less than or equal to this quantity. So this quantity is an upper bound for the output values of the function f on this interval. And therefore, its least upper bound, which is mu plus delta over 2, must be less than or equal to this upper bound. And this quantity is less than mb. So this shows mu plus delta over 2 is less than mb. And that tells us u plus delta over 2 satisfies the requirement to be an element of S. So u plus delta over 2 is an element of S. But that contradicts the fact that u is an upper bound of S. So this completes the case u is less than b. Now let's consider the case u is equal to b. Now in the case u is equal to b, we're going to have a similar argument as case 1 actually. So the idea is, since f is continuous at every real number in a comma b, well in particular, f is continuous at b, or u is equal to b, so it doesn't matter which one you use here, but I'm going to just say b instead, so replacing all the u's with b. Since f is continuous at b, this means that this statement is true, right? And this statement works for every positive real number. So in particular, it must work for the positive real number mb minus f of u over 2. Remember, we're still assuming for a contradiction, f of u is less than mb. So taking epsilon to be mb minus f of u over 2, there exists a positive real number, I'll call eta, such that for all x in a comma b, if asked value of x minus b is less than eta, then asked value of f of x minus f of b is less than mb minus f of u over 2. But then, in this case, u is equal to b, so b is the least upper bound of S. So anything smaller than b is not an upper bound of S. So in particular, b minus eta is not an upper bound of S. And since b minus eta is not an upper bound of S, this means that b minus eta is not greater than or equal to every element of S. Instead, b minus eta must be strictly less than some element of S. And I'll call that element W. And since b is an upper bound of S, we know that b is greater than or equal to every element of S. So in particular, b is greater than or equal to W. Now to reach a contradiction, what we are doing here is as follows. Again, we consider the closed interval a comma b, but in this case, b is equal to u. And what we've done here is we've considered an eta neighborhood of b, and we have chosen some element w and s that is between b minus eta and b. Now if we take any element between a and w and send it into the function f, its output value is going to be less than or equal to mw. And mw is less than mb, because that's what it means by definition for w to be an element of S. We have mw is less than mb. But how does this neighborhood work? Well, if we take any element from b minus eta to b and send it into the function f, well then this inequality will tell us that the output value is going to be less than the average of mb and f of u, just like we did in the previous case. And that's less than mb. So, no matter what, if we take any element between a and b and send it into the function f, we're always going to be either less than or equal to mw or less than mb plus f of u over 2. But no matter what, we're always less than or equal to the maximum of mw and mb plus f of u over 2. But since both of these guys are less than mb, well then the maximum must be less than mb. So this is essentially telling us every output value of the function f will be less than or equal to this quantity. So this quantity is an upper bound for the function f. But since mb is the least upper bound of the function f, mb must be less than or equal to this upper bound. So we get mb is less than or equal to this quantity, which is less than mb. So we have mb is less than mb, which is a contradiction, right? So that's essentially our plan here to reach a contradiction. So if we consider an arbitrary element x in a comma b, well then we have two possibilities. Either x is less than or equal to w or x is greater than w. If x is less than or equal to w, well then we have x is greater than or equal to a and x is less than or equal to w. So x is an element of the closed interval a comma w. But this means when we send x into the function f, f of x is going to be less than or equal to the least upper bound of the output values of f over a comma w. Or in other words, that's saying f of x is less than or equal to mw. And since w is an element of s, by definition of s, mw is less than mb. Okay, so yeah, that's what happens if x is less than or equal to w. Now let's consider the case x is greater than w. If x is greater than w, well then we have b minus eta is less than w is less than x, which is less than or equal to b, which is less than b plus eta. So this tells us x lies between b minus eta and b plus eta. And from properties of absolute values, that tells us the absolute value of x minus b is less than eta. And because absolute value of x minus b is less than eta, well from here, that implies absolute value of f of x minus f of b is less than mb minus f of u over 2. But remember, this is going to imply that f of x is less than the average of mb and f of u from the same argument that we gave last time, right? We know that f of x minus f of b is less than or equal to its absolute value. So f of x minus f of b must be less than this quantity. So then, adding f of b to the other side, what do we get? We get this, but when we combine these two guys together into a single fraction, this is just mb plus f of u over 2. Remember, b is equal to u, so f of b is just f of u, so the f of u, f of b are just going to combine together like this. So we're going to get f of x is less than the average of mb and f of u. And we know that this is less than mb. So what this tells us is, if x is any element of a comma b, then no matter what, we either have f of x is less than or equal to mw, or f of x is less than mb plus f of u over 2. And therefore, f of x must be less than or equal to the maximum of mw and mb plus f of u over 2. But since these two guys are both less than mb, their maximum must be less than mb. And so, what does this tell us? Given any element x in a comma b, f of x is less than or equal to this quantity. So this quantity is an upper bound of the function f over its entire domain. Remember, mb is the least upper bound of all of the output values of f. So mb must be less than or equal to this upper bound. So we have mb is less than mb, which is absurd, right? mb is equal to mb, so we have a contradiction. So we have mb is less than mb, so we've reached a contradiction. So in either case, whether u is equal to b or u is strictly less than b, we reached a contradiction. But that means, no matter what, we reach a contradiction. Our assumption that f of u is less than mb led us to a contradiction. But from earlier, remember, we know f of u is less than or equal to mb, because mb is greater than or equal to every output value of f. So since we've eliminated the possibility that f of u is less than mb, we must have f of u equal to mb. So we have that mb is an output value of the function f. But remember, that was enough to say that mb is the maximum value for f, because we know that mb is greater than or equal to every output value of f, but we've just shown mb is itself an output value of f. Therefore, mb must be the maximum value for f. And so we're done. This completes the proof. And so yeah, that's pretty much it for this video.